Well, guys, our boogeyman has returned. That means we are battling our archenemy, stoichiometry, once again. So this time it's in the context of um, energy. So basically, to get started, it says that for any reaction, we have not talked about this much for this entire school year yet, but energy is a function of every single chemical reaction. So if energy is going to be released, then what that's going to be, as you probably already know, is going to be an exothermic reaction. Now, on the other hand, you already know that if energy is absorbed, then, wow, then that will be an endothermic reaction. Okay, so again, that's just review. We learned that already earlier this unit several times over. So what we have here is a a combustion reaction. It should look pretty familiar because this is basically cellular respiration from last year in biology. But what is most notable about this equation in this context is this right here. We don't normally include that. We always have the glucose plus the oxygen required to burn. We have the two products of every single combustion reaction, which is carbon dioxide and water. But what we have included this time is the amount of energy that is released during a cellular respiration reaction. So in this case, notice that the kilojoules, the energy is on the right side of the arrow. If it's on the right side of the arrow, then energy is released. Wow, let me start that over again. So energy is going to be released because the word or the number of kilojoules is on the right side of the arrow. So again, if the kilojoules is on the left side of the arrow, then it would be going into the reaction. It would be absorbed into the reaction. Therefore, that would be endothermic. Okay. So now let's go ahead and try one of these problems. So what we have again, stoichiometry. Before we get too far, don't worry. This is not going to be nearly as bad as some of the stuff we've done in the past, and you'll see very quickly. So it's asking how much heat is released when 1 mole of glucose is combusted. Now, combusted just refers to this because this, again, is a combustion reaction. Don't let that verb throw you. It's just, again, explaining the reaction. What we're going to do, like we always do in stoichiometry, is we're going to start with whatever number, unit, and compound that we're given to begin with. So that's C6H12O6. So just like always, what I'm going to do is I'm going to start a fraction over here. I'm going to go ahead and move my unit and my compound down to the bottom right in order to cancel out. So that's mole of C6H12O6. Then above that, what I'm going to do is I'm going to try to convert either into grams or into moles of something else. Or in this case, what I could do is I could just go ahead and go straight into my kilojoules. Why I could do that is because I know the conversion factor of kilojoules to moles of glucose. How do I know that? Because they're tied in the same chemical equation. Again, if they were not in the same chemical equation, then I would have no clue of what to do. But in this case, I do because it's all spelled out for us. What I'm going to do is I'm going to go ahead and put 1 mole down here because there's only 1 mole of glucose. Then what I'm going to do is I'm going to put the number of kilojoules right above it according to this equation. Again, I'm getting that right from here. Now, what is going to be a little bit different is I'm going to make it negative. Now, why am I going to make that negative is because, again, like I told you before, and it's all because of this, that energy is being released. Energy is on the left side of the arrow, it's going to be the right side of the arrow, therefore it's being released, so this has to be negative. If kilojoules is on the left side of the arrow, if it was over here, then I would make it a positive value because it would be absorbed. So we got to be really careful with this type of problem because whenever we are putting the kilojoules into our stoichiometry, we have to assign the correct sign. If it is on the left side of the arrow, you're absorbing it. So whatever the kilojoule number is, it will be positive. And if the reaction is exothermic, meaning the number of kilojoules is on the right side, then it's an exothermic reaction. Therefore, no matter what the number is, you have to make it a negative. So now that we have everything in the correct place, I'm going to go ahead and cancel out my moles of glucose, meaning whatever I get, it will be left with just a unit of kilojoules, which is, of course, a unit of energy, thermal energy for that matter. So I'm going to take 1, multiply that by negative 2,560. Just for good measure, I'm going to go ahead and divide that by 1, just so you guys remember how to do this. You multiply across the top, divide down. But basically, this shouldn't be surprising. We get the exact same number because it's multiplied by 1 and divided by 1. So how many kilojoules do you need to combust 1 mole of glucose? Well, again, because there's only 1 mole, then of course this is the number, but it is negative because it is being released. All right, so that is our very first example of how to do a energy stoichiometry problem. Next one, again, is not much more complicated. It says how much heat is released when you have 3 moles of oxygen, okay? Not glucose, this time oxygen. So I'm going to take, very similarly, I'm going to take my number, my unit, and my compound, and then I'm going to go ahead and move my unit and my compound down here in order to cancel out. Again, I need to convert up. I need to have some sort of relationship so I could go from oxygen into my heat. Heat, of course, is my kilojoules. So I'm going to go ahead and put my kilojoules here. I'm going to go ahead and put the number 2560. And again, it's on the right side of the arrow, so that has to be negative. And that is equal to how many moles of oxygen? There are 6 moles of oxygen. 6 moles of oxygen, okay? So therefore, I'm going to get my calculator out again. I'm going to go 3 times negative 2,560 divided by 6. Again, those of you who are good with math, you know that basically we're going to divide it in 2. Again, if that doesn't make sense, pardon me, don't worry about it, but you can just do it in the calculator. But some of you guys are good enough at math that you could recognize what's going to happen already just by looking at what we're multiplying and dividing by. Nevertheless, that is the number of kilojoules or heat that would be released when we combust 3 moles of oxygen, assuming, of course, excess glucose. Okay, there's our very first examples. I'm going to go ahead and erase this. That way I could move down and slide down a little bit further. So now it's going to say, well, what is the reverse reaction and what would that do? So the reverse reaction would be the exact opposite. So I'm going to go ahead and do 6 moles of water. Actually, let me start at the very beginning of my former products, new reactants. 6 moles of carbon dioxide, plus I'm going to make that into 6 moles of water. That is going to also be, I'm just writing the equation from above exactly backwards. That's all I'm doing. I'm not doing anything tricky. I'm just starting with the right side. Now I'm going to write what was on the left, but I'm going to put it onto the right side. So C6 H12O6. Again, I'm just flipping the reaction around. That's all, guys. And that would be 6 moles of oxygen. So moving on, what we need to do, of course, is notice that this is now on the left side. If that is now on the left side, then what that means is this is now an endothermic reaction. Therefore, this energy is being absorbed. So here in a minute, when I start putting this into a stoichiometric calculation, you'll notice that the sign of my kilojoules will become positive because it's on the left side. So let me show you what I mean. How much energy is needed to produce 12 moles of glucose? So I'm going to go ahead and do what I always do, 12 moles of glucose, because that's what they gave us to start with, C6, H12, O6. I'm going to go ahead and move my moles of glucose down here to cancel out. Again, by this time of the semester, guys, I hope this becomes second nature. Then as I go up, I need to convert into something, again, because it's all tied into the same chemical reaction. I could go ahead and put my kilojoules right there. So how many moles of glucose do I have? My glucose is now on this side. So here's my glucose. I don't see any number in front. Therefore, it's still going to be 1. My number of kilojoules, of course, is located right here. Now it's on the left side of the arrow. So it's going to be 2,560 kilojoules. But this time it's going to be a positive value because it's on the left side. This will cancel out with this. So basically, it's going to be 12 times 2,560 positive. And that's going to give me a very large number, which is 30,720 joules. No, actually, it's kilojoules, isn't it? Yeah, that's a very large amount of energy. So that's the amount of energy that you would get. Again, that will be a positive value. That's the amount of energy that would be needed to be consumed in order to combust 12 moles of glucose, okay? So again, you'll notice that this is really not very difficult at all. The only thing we need to be careful with is when we're putting in the kilojoules into our stoichiometric conversion, we do have to make sure that we use the appropriate sign. Okay, moving on. So we need to determine whether this reaction is endo or exothermic. Again, to do so, you will notice that this right here is on the right side. If it's on the right side, then it's going to be exothermic, right? And it's going to be, our delta H is going to be 390. I'm going to pause on that. Yeah, sorry, 393.5. I'm sorry, guys. I just was second guessing myself. I apologize. Yep, so that would be that. And again, it's on the right side, so that would be negative. Then on the bottom reaction, what we have is the kilojoules is now on the left side, right here. Therefore, it's going to be endothermic, and it would be 176 kilojoules. But this time, it's going to be a positive value because it's on the left side of the arrow, which of course represents the reaction. Let's go ahead and knock these last two out, and then we'll call it a day for this video. So calculate the amount of energy involved when 15 grams of water is produced. So what I'm going to go ahead and do is I'm going to take, as always, 15 grams of water, H2O. I'm going to go ahead and move my grams of H2O down here. Then I need to go into moles of H2O because, again, we cannot go directly from grams into kilojoules because, as I told you guys many times before this semester in the school year, is the masses of every single compound is different. So we must always go through moles. So what I'm going to do is I'm going to find for every 1 mole of water, I'm going to calculate using the periodic table the molar mass of water. So the mass of 2 hydrogens and 1 oxygen added all together. What that comes out to be is 18.015. Okay, now I'm going to cancel out my grams of water and grams of water. So now I'm into moles of water, but they want energy. So I need to go ahead and go one more step. I'm going to move moles of water down here. Now that I'm in moles of water, I could go directly into kilojoules. So I'm going to put kilojoules there for every, oh, I'm sorry, I drew that line incorrectly. I apologize. So I'm going from here to here. So I need to look at my moles. So for every 2 moles of water, I'm going to have 572 kilojoules. But again, is that a positive or negative value? 572 is on the right side. Therefore, it is a negative value. So I'm going to go ahead and cancel out my moles of water, leaving me with only kilojoules. So I'm going to take my calculator. I'm going to do 15.0 times 1 times negative 572. I'm going to divide that by 18.015. I'm going to divide that again by 2. And what I get is my final answer of negative 238.13. I'll call that a 5. And that would be kilojoules. And there's my answer for my amount of energy needed to produce 15 grams of water, according to the equation above, okay? So this is just a little bit harder in that we had to go from grams into moles, like we've done countless times, and then from moles into kilojoules, like we just learned on the page just above. Last one, we have calculated the amount of energy involved when 3.75 moles of aluminum oxide is decomposed. Again, as you guys know, decomposed just refers to a decomposition reaction. It's not anything to worry about. What I am going to do is take my 3.75 moles of aluminum oxide, which is Al2O3. That's supposed to be a 3. Let me try to fix that. Then I'm going to take my moles of Al2O3, and we want how much energy. So since we're already in moles, I could go directly into kilojoules, unlike number 2. I'm going to go ahead and put for how many moles of aluminum oxide? I see 2 moles of aluminum oxide. Then how many kilojoules? I see 300 or 3,352. It's on the left side, so that's a positive value. Let me try to clean that up just a bit because that's really sloppy. So that's a times, and that's a positive value. That looks like a 4. So wow, I'm just doing it worse. There we go, I guess. Moles of aluminum oxide, 3.75 times positive 3,352. And I'm going to divide that by 2. And I get my final answer, which is a positive 6,285 kilojoules. And again, that's a positive value. And there's the amount of energy that is needed to be consumed in order to decompose 3.75 moles of aluminum oxide. All right, guys, as always, thank you for watching. That is energy stoichiometry.